Welcome back to Scholars Universal online class. I will be treating electric field part 3, which is calculation involving series and parallel connection of resistors. Now, it is possible we have more than one resistor in an electric circuit. You can have 1, 2, 3, 5, 10 resistors in an electric circuit. And such resistors may be connected in parallel and in series. So we're talking about the series connection and parallel connection of resistors. And now we find the effective resistance when resistors are connected in series and equally when they are connected in parallel. Okay, let us start with series connection of resistors. Now, when resistors are connected in series, it means that they are connected end to end, as it has been rightly shown here. Now, when you have resistors connected end to end, when this resistor, the end of this resistor is connected to the end of the next resistor. Now, such connection is what we refer to as series connection. Now, this is also another example of series connection. The resistor R1 here, the end of this resistor R1 here is connected to the other end of this resistor R2. Now, also, the end of this resistor R2 is connected to the end of this resistor R3. So when we have resistors connected in this manner, it is said to be in series. Now, when we have resistors in series, there are some vital points we should know before we go into calculations. Now, when we have resistors in series, it is observed that you have same current flowing through each and every of those resistors. The same current. The current you have flowing through this resistor R1 is the same current that will flow through this resistor R2. But there's going to be a difference in the voltage across each of the resistor. There's a voltage drop across each of those resistor. So I said we should take note that we have same current flowing through the resistors when they are connected in series, but you have different voltage across each and every of the individual resistance that you have there. Now, by Ohm's law, we'll deal with Ohm's law in the next very soon now. Now, Ohm's law gives a relationship between the current and the voltage drop across a conductor. Now, Ohm's law is mathematically given as your potential difference V equals your current multiplied by the resistance. Now, the total PD would use this as an example, would use this diagram as an example. Now, the total potential difference across this resistor R1, R2, R3, and R4 is going to be the sum of the voltage drop across each and every of those resistors. That is what we have here, that the total PDV is equal to V1 plus V2 plus V3 plus V4. V1 voltage drop across resistor 1, V2 voltage drop across resistor 2, and so on. And remember from the Ohm's law, we said that your potential difference is equal to the multiplication of your current and the resistance. So we can have that the total PD, which is this IR, the subscript C, signifying the total PD across the circuit, is IR1, which is the voltage drop across resistor 1, IR2 voltage drop across resistor 2. Now, the reason we are using I all through here is because we said we have same current flowing through each and every of those resistors. So if I have current I flowing through resistor 1, I would equally have current I flowing through resistor 2. Now, if I factorize the current out from this equation now, I can have that my IR2 will be equal to I open bracket R1 plus R2 plus R3 plus R4. So if I divide through by the current flowing through the circuit, I have my total resistance to be R1 plus R2 plus R3 plus R4. So if we are to find effective resistance in a series connection of resistor, we will just add up the value of each of the resistance offered by the resistor. We add it up. We add R1, R2, R3, R4. Now let us have an example Now, we have three resistors of resistance 1 ohms, 2 ohms, 4 ohms are connected in series. Now, we have to find the equivalent resistance of the combination. So meaning that the value of the first resistance is 1 ohms, the value of the second is 2, and the value of the third is 4. And like we have rightly proved here, that total resistance is just an addition of each of those resistances. So we can have that total resistance in this series circuit of resistors is just going to be 1 ohm plus 2 ohm plus 4 ohm. So the equivalent resistance offered in this circuit is 7 ohms. Now we can have another example, this is example 2. Now from this diagram, we have to calculate the equivalent resistance in this circuit. So you can see that the value for the resistance in this resistor R1 is 1 kilo ohms. Now that for your second resistor R2 is 2 kilo ohms and your R3 is 6 kilo ohms. Now the potential drop across the three resistors is 9 volts. But for this question, we only have to find the equivalent resistance in the circuit that we have here. Now, we'll just go by the idea that we have gotten from addition of resistors in series. So we just add up individual resistance. So we have 1 kilo ohms plus 2 kilo ohms plus 6 kilo ohms, giving us the total resistance offered, the total opposition offered to the flow of current in this circuit to be 9 kilo ohms. Now, we'll continue with resistors in parallel. When we have resistors connected in parallel. Now, when we have resistors connected in parallel, it means that their terminals are connected to the same two nodes. Now, this is a node. A node is just a junction where we have 3 or more connecting wires coming together. Now, every of those lines that we have here, they are connecting wires. So this is a node, this is a node, this is a node, and this is another node. Now, when you have resistors connected in such a way that their terminals are connected to two same nodes. Now you can see that this resistor is connected to this node and this one is connected, the end of the resistor is connected to this node. So when we have this kind of arrangement, resistors are said to be connected in parallel. Now, one thing we should know in parallel combinations of resistor is that the equivalent or the overall resistance is usually smaller than the smallest resistor that we have there. So when we connect every of these resistors together, the equivalent resistance is usually smaller than even an individual of the resistance that you have there. Now, like we have rightly noted some things in the series connection of resistors. Now, we said in that series connection that you have same current but different potential difference across the resistor. Now, for your parallel connection, you have different current flowing through each and every of these resistors that you have here. You have different current flowing through resistor R1, resistor R2, and R3. But the potential difference across the three resistors that you have here, the R1, R2, R3, same thing with this R1, R2, R3. The potential difference across the three resistors is the same thing, but you have different current flowing. Now that is why we have, like this diagram we have here, we can have I1, I2, I3. So meaning the current flowing, total current flowing through them will be a combination of your I1, I2, and I3. So you have different current flowing through each resistor, but the same potential difference across the resistor. Now, as we have rightly said, that in parallel connection of resistors, we have the same potential difference, the same voltage drop across every of the resistors, and we have different current flowing through each and every of the resistors that we have here. Now, we would like to prove or deduce a formula that would make use of to find the equivalent resistance when we have resistors connected in parallel in the circuit. Okay, now, like we have here, we have the total PD across the circuit to be equal to V1, V2, V3, since we have same potential difference across each resistor. Now, for the current flowing through the resistor, we have that the total current flowing through the circuit is an addition of I1, I2, and I3. I1, the current flowing through resistor 1, I2, current flowing through resistor 2, and I3, current flowing through resistor 3. Now, from Ohm's law, that we have that the potential difference across the circuit is equal to the total current and the total resistance offered to the circuit, the total opposition offered to the flow of current in the circuit. Now, when we make the current submit formula, we have that the current is equal to potential difference divided by the resistance. Now, if I find the current flowing through each resistor, I can have that I1, which is the current flowing through resistor 1, is equal to the voltage drop across resistor 1 divided by the resistance offered by resistor 1. Now, same thing for current flowing through resistor 2 is equal to V2 over R2. Then current through resistor 3 is equal to V3 over R3. But remember that we have said that V1 equals V2 and equals V3, meaning the same potential difference across the three resistors that we have in the circuit. So I can change my V1 that I have here to be V. Since V1 is equal to V, V2 is equal to V, your V3 is also equal to your V. So I can rewrite this formulas to be I1 equals V over R1, I2 equals V over R2, then R3 equals V over R3. Now, coming back to this equation, that your total current is I1 plus R2 plus I3. So you can add this current, and this current. So we have I total to be your I1, which is V over R1, your I2, which is V over R2, your I3, which is V over R3. Now, also, your total current is going to be V, also the total potential difference across the circuit divided by the total resistance offered to the flow of current in the circuit. So if I factorize my potential difference out, my V out, it's going to cancel out each other. So I'll be left with 1 over the total resistance equals to 1 over R1 plus 1 over R2 plus 1 over R3. So when we have resistors connected in parallel, the total resistance is given by 1 over RT. This R subscript C means total resistance offered in the circuit will be 1 over R1, which is the resistor 1, 1 over R2 resistor 2, and 1 over R3 resistor 3. Now let us take an example to show that. Now, the first example, if three resistors, 2 ohms, 3 ohms, and 5 ohms, are connected in parallel in the circuit, now we have to calculate the equivalent resistance of the combination. Now remember that we have shown from this proving that 1 over the reciprocal of the total resistance is reciprocal of resistor 1, then resistor 2, and resistor 3. So making use of that formula here also, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Now we have 1 over RT to be equal to 1 over our R1 here would be the 2 ohms resistor. So 1 over 2 plus 1 over 3 plus 1 over 5. Now solving this one out, we see that the LCM of this is going to be 30, and an addition of this will have 31 over 30. Now the total resistance that we are looking for is not 1 over RT, but RT. So meaning we will find the reciprocal of this 1 over RT, which is RT, and we'll also do same thing to this side. So we'll have this one to be 30 over 31. Now the total resistance offered to the flow of current in this circuit is 0.97 ohms. Now, like I explained earlier, that the total resistance in a parallel combination of resistor is usually lower than the value of this individual resistance. Now we can see that we have a resistor of 2 ohms, 3 ohms, and 5 ohms. When we connected them in parallel, we are getting a total resistance of 0.97 ohms, which is smaller than even the smallest of this resistor. So that is what we have in parallel connection of resistors. Now we can take another question, example 2. Now we have to calculate the effective resistance in this diagram that we have below here. Now obviously we can see that these resistors are connected in parallel. Like I've rightly explained, that a parallel combination is when you have the end of a resistor connected to two nodes. So this is also a parallel combination. Now it is possible we have a combination of series and parallel combination of resistor. I believe when we are given a question like that, we'll be able to find the equivalent resistance. Now for this one, following our formula, which is 1 over R1 plus 1 over R2 plus 1 over R3. So we'll be having 1 over R3, which is our total resistance, to be 1 over 10 ohms, which is the value of the R1, 1 over 2 ohms, the value of R2, and 1 over 1 ohms, which is the value of your R3. Now, adding this together, we have 16 over 10. Now, remember, like we solved the previous question, we are looking for the total resistance, not the reciprocal of the total resistance. So, meaning that we must find reciprocal of this one, which is RT, your total resistance. Equally, we find reciprocal of this also, which is 10 over 16. Now, the total resistance, the total opposition to the flow of current offered in this circuit is 0.625 ohms. Again, we can see that the value of this resistance is lower than even the smallest resistor that you have here, which is 1 ohms. Now you can see that the value of this is 0.625 ohms. Now, we'll now be talking about electrical conduction through materials. Now, we have a law that explains the relationship. We have heard of Ohm's law. Now, we have a law that explains the relationship between the current flowing in the circuit and the potential difference in that circuit. We have said the potential difference is the work done in taking a positive charge from one point to another. So we want to see the relationship between the current flowing in a conductor. And I've rightly told us that potential difference is essential, because if there's no difference between the potential between one end and the other end, current would not flow. So we want to see the relationship between current flow and the potential difference. And the relationship is given by this Ohm's law. Now, Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference across its ends, provided that temperature and other physical conditions are constant. Now, if we have temperature and other conditions constant, in every metallic conductor, the current flowing is always proportional to the potential difference across its ends. So mathematically, we can have that I, which is your current, is directly proportional to the potential difference across the end of the circuit. Now, when we remove the proportional sign, we have that V over I, your potential drop over the current, is equal to a constant. Now, the value of this constant is a measure of the opposition, meaning that the ratio of your potential difference to the current is a constant. That constant is a measure of the resistance, the opposition to the flow of current. So mathematically, we can have that your V over I is equal to R. Your V over I equals to R. Your V over I, which is the potential difference over the current, is equal to the resistance. Remember, potential difference is measured in volts, current is measured in ampere, and resistance is measured in ohms. So I can have that my V equals IR. Now this explains the relationship between your potential difference and your current. And I said the relationship is given by what we call Ohm's law. Now, next thing we're talking about is the factors affecting electrical resistance. Now, we have rightly said that resistance is the opposition to the flow of current, and resistance is usually offered by a resistor. Now, there are some factors that affect resistance of a conductor. Now, we're talking about the four major factors that affect the resistance of a conductor. And the first one is the length of the conductor. Now, the length of a conductor determines the resistance of the conductor. Now, the resistance of the conductor is directly proportional to its length. It means that as the length is increasing, the resistance of the wire is also increasing. So as you increase the length of a conductor, the resistance of that wire is increasing equally. So when I have a conductor that is 1 meter long and a conductor that is 2 meters long, obviously A conductor that is 2 meters long has an higher resistance than the one that is 1 meters long. Now, the second factor that affects the resistance of a conductor is the area of the conductor. Now, the resistance of a conductor is inversely proportional to the area, meaning that as the area is increasing, resistance is decreasing. As the area of a conductor is increasing, the resistance is decreasing. So, meaning the more the area, the less the resistance. The less the area, the more the resistance of a conductor. Now, also temperature. The resistance of a conductor varies directly as the temperature. Now, for certain conductors like metallic conductors, the higher the temperature, the higher the electrical resistance. So, as you increase temperature of a conductor, you are equally increasing the resistance of that conductor. Now, finally, the type of substance of the material. The type of substance of material determines the resistance of the conductor. Now, experience shows that the resistance of a wire maintained at a constant temperature, when temperature is not changing, experiment shows that it is related to its length and cross-sectional area by this expression of R equals rho L over A. Now, this symbol that we have here is what we call rho, R-H-O, rho. Now, this resistance measured in ohms is equal to your rho L. Your L is your length and A is the area. Now, we'll see that from this mathematical expression that we have here, we can see that resistance is inversely proportional to area. Resistance is directly proportional to the length of the conductor. Now, this rho is a constant of proportionality, which we refer to as resistivity. Now, the resistivity depends on the nature of the material. Resistivity is just how a material can allow currents to flow through it. The amount of opposition it can offer to the flow of current. Different materials have different value for resistivity. So, the resistivity is just a measure of the nature of the material. Now, the unit for this resistivity is ohm meter. You can see that when we make resistivity a sort of formula from this equation, we'll see that the unit R is in ohms, area is in meters squared, and length is in meters. Now, when we do this effectively, we'll see that the unit of this resistivity is ohm meter. Now, let us take a question. Now, the question asks us to find the resistivity of a cylindrical material whose 1 meter length has a resistance of 2 ohms. We have to find the resistivity of the cylindrical material whose 1 meter length has a resistance of 2 ohms and diameter of the wire is 0.5 millimeters. Let us take out our parameters. The length of the wire is 1 meters and the diameter is 0.5 millimeters. So we'd have to find the radius. Remember that the radius is your diameter divided by 2. So we are dividing this diameter by 2. So your radius is going to be 0.5 millimeters divided by 2. But remember, the standard unit of your length is meters. So we have to convert this millimeters to meters. So converting this one, we have it to be 2.5 times 10 to the power minus 4 meters. Now, since the nature of the material is a cylindrical material, now the area of the material is going to be the area of a circle. The surface of the material looks like a circle. The surface of a cylinder looks like a circle. So we are going to make use of the area of a circle, which is pi r squared. Now, doing this one, our pi is 22 over 7 and our radius 2.5 times 10 to the power minus 4. So when we do this, and remember that the resistance given in the question is 2 ohms. Now, from our formula that R equals rho L over A, we can make rho sort of formula, which is RA, resistance times area, divided by the length of the conductor. So when we have this, we have our resistance, which is 2 ohms, then multiplied by the value of our pi, 22.7, then multiplied by the radius squared, then the length of the conductor, which is 1 meter. So from this, we get the value of the resistivity of this wire to be 3.93 times 10 to the power minus 7 ohm meter. Remember, the unit for resistivity is ohm meter. So the value for the resistivity is 3.93 times 10 to the power minus 7 ohm meter. Now, we'll be talking about electrical work done in a circuit. In our previous classes, we have talked about what work done is. We define work to be done when a force moves through a particular distance. Work is said to be done when a force moves through a particular distance. So now, electrical work is done when electricity flows from one point to another point of different potential. Remember, we said there must be a potential difference for currents to flow. So meaning that electrical work done is the work done when electricity flows from one point to another point of different potential. Now, the formula for work done is given by the quantity of charge multiplied by the potential difference. And remember that work done is measured in joules. So, and the quantity of electricity is measured in coulombs. And the formula for the quantity of electricity is given by current times your time. Remember, we have defined current to be the rate of flow of charges in a circuit. So the quantity of charge is given by Q equals IT. Q, quantity of charge measured in coulombs, I, current measured in ampere, and T, your time measured in seconds. So then I can have this formula, this work done in a circuit, which is QV. I can replace my Q with IT, I current, T time. So I have my work done to be IVT. I, the current in amperes, V, voltage in volts, T, time in seconds. Okay, now one thing we should know is that there is a conversion of electrical energy from one form to another. Now that explains the principle of conservation of energy, that energy is not created nor destroyed. It is only transformed from a form to another. So electrical energy can be transformed to other forms of energy. Now, one of the transformation is heat energy. Now, electrical energy is transformed into heat energy. For example, electric irons, electric kettles. Now, you see that for electric irons to run, there must be electric energy supplied into the iron. And when electric energy is supplied into the iron, the form of energy that will be formed or produced from the iron is heat energy. Now, another conversion of electrical energy is your mechanical energy. We see that in electric motors, even the blade of fans. Now, when you switch on your fan, you see that electric energy produced from your switch or from your source of electricity is converted to a mechanical energy of the fan, the blade of the fan. Now, also, another example is the glow of filament lamps or your bulbs. Now, electrical energy is transformed into light energy that we see in the glow of filament or that of bulbs. Now, sound energy also, we see that in record players, our home theater that we have, that electrical energy is converted to sound energy. So these are just the few conversions of electrical energy into other forms of energy. Now, we'll be talking about electrical power. Like we have rightly discussed in previous classes, that power is defined as the rate of doing work. So power is defined as work done divided by your time taken. Work done in joules, time taken in seconds. Now remember that your work done, we have defined work done before to be IVT. So if I have IVT divided by my time, I have my power to be equal to IV. The time would cancel out each other. And remember, the unit of power is watts. Now, finally, we'll be talking about how we buy and sell electric power. Our distribution company, be it the IKEDC or IBEDC and some other forms of distribution company. Now, there's a way in which you buy power from them. When they bring the bill to you, there's a way you are being charged to pay for the consumption, energy consumption per month. Now, we'll be dealing with how you buy and sell electric power. Now, we said electrical energy consumption is measured and sold in units of kilowatt hour. Now, 1 kilowatt hour would be, a kilowatt is 10 raised to the power 3 watts, an hour is going to be 60 times 60. So 1 kilowatt hour is going to be 3.6 times 10 raised to the power 6 joules. So meaning that for 1 hour, you have consumed an energy of 3.6 times 10 raised to the power 6 joules in an hour. Now, we could have a simple explanation to that. Now, if your distribution company charges at the rate of maybe 10 kobo per kilowatt hour. Now, the cost of lighting up the room for that period is given by, now, since your distribution company is selling for 10 kobo per kilowatt hour, now the cost to be paying for that hour is going to be 1.2 times 10. So you are paying 12 kobo for making use of that bulb for that period of time. Now let us have a very good question here. Now, calculations involving buying and selling. Now we have a question. Here. A television which is rated 65 watts, a refrigerator which is rated 1.2 kilowatts, and we have electric kettle which is rated 650 watts, then 10 lamps which is 40 watts each. We are told in the question that they are connected in series in a house. Now the question says that how much will it cost the housekeeper to switch on all appliances for 24 hours if the cost of electricity is 15 kobo per kilowatt hour? Now, the first thing we have to do is to find the total energy or total power consumed by this person. Now, the person consumed, the television was switched on for 24 hours. Same thing, the refrigerator for 24 hours. The electric kettle was switched on for 24 hours. Now, we have to find the total power consumed. Now, we have 65 watts for the television plus refrigerator. I have converted my 1.2 kilowatts to 1,200 watts. Remember, kilo is 10 raised to power 3. So I have this to be 1.2 times 10 raised to power 3 watts. So I have it to be 1,200 watts plus 650 watts, which is the rating for the kettle. And I have 10 lamps, which one of it is 40 watts. So for this one, I have that total energy consumed is 2,315 watts. Now, converting this to kilowatts, I divide this by 1,000 to get this in kilowatts. Remember that we said that the energy consumption is in kilowatts. So converting this one to kilowatts, I have 2.315 kilowatts. Now, the energy consumed, remember, energy is power times the time taken. Now, you multiply the power times your time in hours. Energy consumed is in kilowatt hour. So the total energy consumed by this person is 2.315 kilowatts. It consumes 2.315 kilowatts in 24 hours. So we're going to multiply the total energy consumption by the number of hours he actually used in consuming this energy. So I have 2.315 times the 24 hours in which he has used to consume this energy. So I have the energy consumed for the whole day to be 55.56 kilowatt hour. So he has consumed a total energy of 55.56 kilowatt hour for 24 hours. So, and the distribution company is charging him 15 kobo per hour. So meaning that for the 24 hours, we'll be multiplying the total energy he has consumed for the whole 24 hours multiplied by this 15. Now, on doing that, we have gotten 833.4 kobo. So for the whole day, it consumed 833.4 kobo. So converting to naira, we have 8 naira 33 kobo. So for a day, if the switch is on the television, if the television is on, refrigerator is on, the electric kettle and the lamp is on for the whole 24 hours. So for that day, you'll be paying 8 naira 33 kobo. Thank you for learning with us at Scholars Universal School. Assignments and tests will be gotten on WhatsApp. Thank you.